So I think we can start exactly on time today. Welcome to the session on time varying volatility. Yeah, looks like we are a pretty small group at the moment. Maybe a few more people are going to show up. We have 3 talks in total. The first is Robin Kruse-Becher from the Fernuniversität in Hagen. He will be our first presenter. Then we have Cristina Amado from the University of Minho. I hope I pronounced it correctly. And then me at the end. And my name is Laura Reh. I'm a PhD student at the university in Cologne. Okay, so let's start. Robin, the stage is yours.
Yeah, okay. Many thanks. So we are all somehow connected here. Yeah, today's work is joined with Matej, Christoph, and Rob. We are considering predictive regressions under heteroscedasticity. So this is fully qualified. This is a typical data which is used in a predictive regression. On the left-hand side, you have the equity premium, which is here recorded at the quarterly frequency. You can see quite some heteroscedasticity even at that frequency. It's a long data set. And on the right-hand side, lagged by 1 period, you will have a predictor of this kind. Many around. This is one example. It's a book to market ratio. Often their equity premium. What you can immediately see is that the predictor is close to a random walk, so highly persistent, while there is almost no persistence, no autocorrelation in the equity premium, as we should expect. These 2 time series are typically put in a predictive regression. We are not suggesting to do so, but we are picking up the literature at this point. So our point is heteroscedasticity, so we are estimating non-parametrically the volatility in a non-parametric fashion here, entirely non-parametric, I should say, and compare it to the squared equity premium. And as you can see, it tracks the movements overall quite well. So yeah, I have to be very quick. This is a typical roadmap. Yeah, let's see if we can get. So how does the predictive regression? So and XT is generated as an autoregressive process with 0 sizes and in that X is a script for continuous amount. Innovations to this autoregressive key, and important to consider them in connection to the regression disturbance UT. So while we might assume for simplicity that UT and VT are serially uncorrelated over time, we should say something later about their contemporaneous correlation. So UT and VT, yeah, they are very likely in this setup not to be uncorrelated. So what is the nil hypothesis of interest? Well, of course, we want to know whether this predictor X helps in any case for predicting YT. So it's quite well known that OLS estimation and testing might be problematic. Why is that? Well, because of this contemporaneous relation between the regression disturbance and the predictor innovation. This is coined endogeneity. Yeah, and later we will also see instruments. So, but what happens first? So we have 2 remarkable features. We have this endogeneity, and we also have very high persistence, which we can model, for instance, via near integration. So you have a local to unity autoregressive term, Well, what happens with your t-statistic? Well, that converges in distribution to a mix between two things. One is by an Ornstein-Uhlenbeck process with the localization parameter C, reflecting the very high persistence in the predictor. And then we also have a nicely behaved random variable Z. And the delta is here the contemporaneous correlation between UT and VT. So you can see immediately that this has an impact. On the other hand, if delta is equal to 0, you can see that things are getting very nicely. On the other hand, as you will see via simulations as an illustration in a second, things also get much easier if you wouldn't have a predictor. So we take first a look at the data very quickly. We do an OLS regression. You can also R squared, which is very typical in that kind of literature. But you get at least a, say, significant naive t-statistic. If you do a heteroscedasticity correction on the standard errors, you lose that result. Let's take a look at that later. So just confirming that the predictor is really highly persistent, we estimate an AR parameter close to unity. The sophisticated unit root test does not reject really, so it's a borderline decision. Okay, the regression disturbance is almost uncorrelated, but strongly heteroscedastic, and the estimated correlation between the two objects of interest here is indeed very negative. So the setup is given, and this is what happens. And you have this strong negative correlation. And as you can guess, we are not favorable. This is telling us that the t-statistic is not following a standard normal distribution as indicated by red line. Typically beta, though the true beta is equal spuriously, and we are concluding that there could be some predictability, but there isn't any. Okay, if you add variance breaks to the data generating process, things just get a bit worse. So what we are suggesting is to estimate the volatility non-parametrically and to in the good old days at least squares. We do that. Oh,
yeah.
My voice isn't doing well.
It's not that clear. Maybe you turn off your video. This sometimes helps a lot.
So where did you lose me?
We understand you all the time, but with interruptions.
Okay,
yeah.
I'm just moving somewhere else then. Okay, please inform me if it doesn't get any better. Okay, so sorry for that. Well, if you do weighted least squares regression instead, you also lose the evidence for any kind of predictability. And that is not really depending on whether you correct for any remaining heteroscedasticity. Maybe there shouldn't be any because we have already filtered it out. So the question is that the solution? Well, no, the estimation might improve, but the testing problem, of course, remains. So what can you do? You can instead use an instrument, as I have already promised. We talk about endogeneity, so we come up with an instrument. The instrument search here is much simplified compared to the usual case. So here we use a self-generated instrument. If you recall the graphs, we can have this endogeneity problem. But things get much better if we would have low persistence. So the idea is very simple here. You are stripping off some, not all, but some of the persistence in the predictor. So you are taking the same variable, but you reduce its persistence. So what you get is a decisively less persistent instrument. Yeah, so it qualifies as instrument validity. And if you do not rip off all the autocorrelation, then it's still correlated with the predictor. So it's a relevant instrument. You can also do more than one instrument, okay, but here's just an illustration. This is the so-called IVX trick. Yeah, you just reduce a bit of the persistence and that's it. So, yeah, Breitung and Dimitrescu came up with an idea of using a two-stage least squares approach where you use more than one instrument. They distinguish type 1 and type 2 instruments. The idea here is that inference gets much better if you add a second instrument, which is a sine instrument here, which is also persistent but exogenous. There are a number of conditions to be satisfied with these kind of instruments, but well, that works. Okay, well, you could then look, as the authors did, at a t-statistic where you use some heteroscedasticity corrected standard errors, and you get a very nice chi-squared limiting distribution for the squared t-statistic. So you could stop here. Yeah. But our approach is not to robustify statistics against heteroscedasticity, but we want to improve directly estimation and inference by using weighted least squares and weighted IVX methods. The idea of using weighted instrumental variables is not new. Kvyat and Feng have a discussion on that. The idea to combine weighted least squares with still HC standard errors, as which we are going to do, is also considered in Romano and Wolf. And Joachim Westerlund and his co-author, they have considered predictive regressions also in the conditional heteroscedasticity framework. And the WLS idea is also picked up in the financial predictive regression literature already. So this is the motivation for using IV methods with heteroscedasticity weights. This is the story. So we come up with a new set of tests. We have to prove that estimating the volatility non-parametrically is allowed. And then we have to show in simulations that we get a good size performance and a power improvement. In the matter of time, I have to be very quick on this. So given some regularity conditions, we use a straightforward estimator from a related paper in econometric theory, use cross-validation for selecting the bandwidth, and we assume that the estimator is adapted to its true value. I cannot go into the technical details here, sorry for that. Well, we come up with a modified version of the IVX estimator. I have to say that the handling of the intercept needs extra care. Before we just had demeaned objects. Here you cannot demean anymore in that simple fashion because the WLS, the 1 over HT adjustment also affects the intercept. So some extra care is needed here, just to say that. We use an HC covariance matrix estimator. I've also mentioned that. So we follow the Kvyat and Feng and Romano-Wolf idea. And we come up with our modified statistic. And we also get the same nice chi-squared 1 limiting distribution for inference. Moreover, we can work out local alternatives. So what is important here is that we take local to zero predictability alternatives. If there is any predictability, it will be close to 0. So you see the beta is in a local to 0 environment. And what is very important is that in these objects, you see this H. And H is the volatility process, which means that the limiting distribution is affected by H, which also means that if you estimate this guy, then you can improve on the power. Well, Monte Carlo, well, we have a very standard setup with quite some variations. We start with the estimation part. So, few things to note. If you have homoscedasticity and it is unnecessary to apply weighted least squares over OLS, you do not lose anything. Yeah. And if you apply weighted IVX, same procedure. Under heteroscedasticity, on the contrary, you can only win, and you can win up to 38%, depending on the persistence of the predictor. So that is kind of the accuracy. Thanks, 5 minutes. Okay, so what about size performance? Well, there is already an IVX statistic around. This is the first column. It's a bit upward sized. Yeah, we have a weighted version of this, doing a little bit better, and we have an I is the infeasible version, where we know the true volatility process instead of estimating it. So this gives, like, say, the infeasible counterpart. You can see some differences here, but what is more important is our essential suggestion is to use more than one instrument. So either you combine the IVX with a sign instrument, that's the S, or with an F. Well, this is Breitung's and Dimitrescu's suggestion, but we do the weighted version. So you can see the size performance is quite good, around 5%. Now, what is it paying off in terms of power? Well, I'm sorry, that was heteroscedasticity as well. Same story, I should say. Yeah. Okay, now the power, if there is homoscedasticity, they perform almost the same. I cannot see any difference here between the blue and the red line. There is a red line beneath the blue line. There isn't any difference. If we zoom in, it's even more trustworthy. There are only very negligible differences. Now, what about the heteroscedasticity case? The blue line is the infeasible. Let's say in that situation, from that test, the maximal power we can achieve. The red line is what we get if we estimate the volatility in the way we propose it. And the black line would be the case if you ignore it. Yeah, so you can gain definitely power here. Okay, that's the story. So the job is done. We can go to the empirics, and see what happens here. Same data, same tests. So the interesting thing here is the following. If you apply the standard IVX, you get test statistics of 1.7 and 2.2. You compare it to the critical values and do not find any evidence for predictability. If you, in turn, use more than one instrument, but you do not weight the data, you get test statistics of 2.69 or 2.88. Both of them, just borderline significant at the 10% level. One is, one isn't. And now if you weight in accordance as we suggested, you get, without any doubt, a significant result. So that is in sample. What about out of sample predictability? I hope I have the minutes for that. So we take the period from 2004 to 2018, 60 quarters, we do one step ahead predictions and do what is done in the literature. We take a naive approach where the beta is equal to 0. And on the contrary, we use a possibly non-zero beta and estimate the beta in different versions. OLS gives an R squared of 1.3, and you can see that, well, in that range, 2.35% is always is already an improvement. So what about a time varying perspective here? If you look at a recursive comparison between weighted IVX and weighted least squares, you can see they perform almost similar before the crisis, around 2008. And then when the crisis hits in and volatility gets even stronger, we have very strong heteroscedasticity in that period, then you can see also differences there. Okay, well, let me conclude. The predictability of equity premium is still elusive. Heteroscedasticity plays a certain role. We aim to exploit heteroscedasticity. Now, we do not see this as a problem, but as a potential for improving estimation and inference. We have done that in the IVX framework, and we could show theoretically the validity of our approach, and via simulations the performance, in terms of size and better power, and the empirics conclude this result. Thank you very much for your attention. I'm happy for any kind of questions or comments.
Thank you, Robin. Unfortunately, we do not really have time for questions. Yeah, you were right on time, but maybe we can postpone that to the end of the meeting or after the meeting.
Yeah, I'm also available on the chat.
Yeah, maybe.
Directly.
Yeah, this is also a nice idea. All right, then let's move to our next speaker. Yeah, I think first Robin needs to unshare his screen, and then we can go on. Okay, now you can try, Christina.
Yes. All right. So good afternoon, everyone. So thank you very much for having me here. And my talk is about multiplicative non-stationary volatility models with exogenous information. So this paper is an extension of what I've been working on, namely on multiplicative models of volatility with a multiplicative decomposition. So I'll start with the motivation. I'll see where I also can do in 20 minutes. I'll probably skip some technical details in between. Well, I'll start with the motivation of non-stationarity, namely that, well, one of the stylized facts that we observed in many long return series. So given if we have a very long series, it's very likely that structural breaks, smooth transitions, smooth changes occur during a very long period, a sample period of series. What we observe is a very slow decaying of the sample autocorrelations of the absolute or the squared returns of financial data. And this can be, of course, the literatures will, some branch of the literature will say this: we have long memory behavior in volatility, or it could also be due to the fact that we have neglected the deterministic shifts in the unconditional variance of these very long return series. So there are some references in the literature, such as Granger and Jung in 2004, Diebold and Inu in 2001, and Mikosh and Staritsa in 2004, where they actually prove or show theoretically or using simulations, if we neglect shifts in the long run volatility, this can mimic the very high persistence behavior in volatility. There are more references in the literature about consequences of ignoring breaks in the unconditional variance, such as Diebold in 1986, Lamoureux and Lantrappe in 1990. The idea is that well, I've been working on this for a few years now. The idea is that is the assumption of parameter constancy valid in Garch models when we are working in a very long return series? And the conclusion is that, given the work that I've been doing and also in the literature, that's very restrictive assumption. So what I propose is that we consider volatility as having short memory, but intensities of perturbations is changing over time. So we include or allow for non-stationarity in the model. There are quite a few proposals in the literature, very flexible Garch specifications proposed in the literature, where they model changes in the amplitude of clusters of volatility, allowing for changes in the volatility in the long run. So there are quite a few approaches in the univariate case, and I have some references here in this slide. some on the non-parametric case, such as the Van Bellingen and von Sachs in 2004, where they also allow for a multiplicative decomposition in the variance into two components, in the deterministic component, that is a function of time, and another component that is a stochastic component, stochastic conditional variance, where that describes the short-run dynamics in volatility. So they call this model the time-modulated gauge. And then there are other approaches such as the spline gauge proposed by Engel and Rangel 2008, is also quite popular in this sort of literature. Brownlees and Gallo also they proposed a similar type of model, but with different splines. And then the multiplicative time-varying gauge model by myself and Timo Terazvirta in 2013. And we also have another paper in 2017, where we also propose this multiplicative decomposition, but instead of using splines, we use logistic transition functions, and the model is parametric. It's a parametric type of model. There is a survey of models with multiplicative decomposition on variances by myself, Silvenoina and Terazvirta 2019. So focusing on these univariate approaches of this multiplicative decomposition variance. So in this paper, what I propose is that we extend this multiplicative structure of the model, where instead of using just time series information, we can introduce some exogenous information to the gauge model. So using this multiplicative structure of the model. So while we are very much aware that volatility or uncertainty about fundamentals are also potential factors affecting market volatility, and there are some references in the literature. These are the most well-known, the ones that I have in this slide: Schwartz in 1989, Bloom 2014, David and Veronese in 2004, and even Engel and Rangel, their paper about spline gauge models, they also have studied this exogenous information. How does it affect time-varying volatility? So there we could think about several measures of macroeconomic volatility for accounting this uncertainty. I'm not so focused in this presentation today on these measures or what type of exogenous information we could think about introducing in the model, but it is more about the modeling framework that I'm going to focus on the presentation. So a possibility would be, for instance, could be choosing, for instance, the Chicago Board Options Exchange Volatility Index, such as the VIX, or some interest rates, or some functions of past values of return series, past conditional variance of the index returns as this stochastic variable that allows for changes in the volatility regimes. So I will go now for introduce now the model, and then propose the testing sequence. How do we, whether we actually need to introduce this information, exogenous information, whether this multiplicative decomposition of the model is actually needed or not. And how we do this is using a sequence of Lagrange multiplier tests. And I will show you some simulation results. I will try to give you some small illustration. It's not finalized this yet, so I'll just illustrate with the application of the tests. So I'm working on this right now. Actually, we'll be working in a few days again. So the model, let's assume we have a return series model. See the time. We have a return series that is modeled as a YT variable. And this YT variable is given as the epsilon t. So epsilon t can be a sequence of random variables. And these random variables are decomposed multiplicatively by this equation number 1. So they are independent, but they are not identically distributed. And the multiplicative decomposition of the variance given by the equation number 2 is given by this product of functions, where HT describes the short-run dynamics of volatility, and it can be modeled by, we could think about a Garch-PQ model. And the GT function is a non-stationary deterministic component, where it's a function of the time. So this function that you can see here is a linear combination of logistic transition functions, and the logistic transition functions are given by this capital G. That is a function of the scale time. So this time is between 0 and 1, and this is relevant or is important in order for us to have a good, asymptotic results. Besides time, so time is basically the variable, the transition variable that is driven the changes in the volatility regimes. Then we have two more parameters, or two more set of parameters, such as the gamma, that is that controls the smoothness of the change in the different regimes, and then the vector of locations, that is the C, where it tells us where these changes in the different regimes occur. So this is a deterministic component of time. And then we have this FT, that is a positive function also, and it's a function of the exogenous information, where again we have a linear combination of these logistic transition functions. We could think about any other type of function here, and this is my proposal, including the logistic transition functions. We could think about any other type of function in this, either in function 4, in the component 4, or in the component 5. So in component 5, where we had this exogenous information, that is given by the variable st. I'm assuming that this variable is weakly stationary, is a stochastic variable. And again, we have the same set, similar set of parameters, the gamma and the C. So we have a nested case here, a special case when this function ft equals 1, then we have the model that is the multiplicative time varying Garch model of myself and Timo Terazvirta when ft equals 1. Of course, we have here some identification problems, and we can sort these problems with the parameters delta naught. We have this multiplicative decomposition, so we could fix, when we are estimating the model, either we could fix this delta so that we have some sort of flexibility given this in the estimation process, or we could just set this delta naught equal to 1. So the logistic transition function is a function of a few parameters, such as the gamma, as I mentioned before, such as the location parameters. So this is the most general function, bounded between 0 and 1, is a continuous function. And then we have some identification restrictions that we have to impose. This is the general logistic transition function, where this k will give us some sort of flexibility with respect to the shape of the transition function. So we could have different shapes of the functions, the function depending how many location parameters. So if you look at these plots, the left plot, we have just one location parameter, c, at equals 0.5, and then we have on the right hand side 2 location parameters and 4 different smoothness parameters. So I'm going to skip this here. And then regarding the test, so I have, I think, 5 minutes. Regarding the test or the sequence of tests, we could think about several alternatives, how the specification of this model could proceed. Well, we could extend the already known this time varying gauge model to have another extra component. So this test against this FT component. If it's so, then the null hypothesis will have Ft equals to 1, and under the alternative we'll have the most simple specification for that F component, where we introduce the exogenous information, or we could extend the gauge, start with the gauge case, and then we could think about extending this into a multiplicative decomposition, into a non-stationary component, and also a stochastic and a component in introducing a stochastic observable exogenous variable. Or we could start from a gauge model to have a multiplicative component function of an exogenous variable. So how do we deal with these different alternatives? Will be by simulations. And how do we do this? With the simulations, I am still working on the simulations strategies using these 3 different alternatives. So this will be studied and developed by simulation. So the test is, so we could think about just by looking at the first alternative, testing for a TV gauge against an additional exogenous variable. This is the most general framework of the model, where we could think about extending in the F component S logistic transition functions against S+1 logistic transitions. That is the component that is a function of the exogenous variable. And we do this by testing whether the gamma equals 0. We have to redefine, so make some sort of transformation in the logistic transition function. And this is the reparameterization that I have done in the logistic transition function. We do this using a Lagrange multiplier test, where you just estimate the restricted model. Of course, we have some identification problem, and this is sorted out by expanding the logistic transition function into a Taylor series approximation under the null hypothesis. And so this implies that our new null hypothesis becomes testing these coefficients θ1 star up to θk star. So if these coefficients are all equal to 0, there's no need to add an extra transition function in the F component, and we just remain with the S logistic transition functions. So this is done, as I mentioned, using a Lagrange multiplier test, and we show that this is a asymptotic chi-square distribution. Of course, this test is not robust to deviations, to the distributional assumptions, well, such as normality or heteroscedasticity and so on. So we apply a robust, let me see if I have, I have 1 more minute. Just, yes, 1 more minute, okay. And then the robust statistics are computed as in Ullrich 1991. So simulations, the simulations work very good for this alternative one. I actually have for other 2 alternatives. And you can see, for instance, 5% nominal size, 4 different DGPs, just well, to show you how this could work for high persistence cases, simulating this DGP2 or DGP3, even for 1,000 observations, we have very good size results. And then we could also think for do the same kind of procedure for the other 2 alternatives. I'm going to skip this, but the procedure is very similar. It just depends on the type of alternatives we are in. We are interested in doing. So different simulation studies for different alternatives. And this, how we are going to model whether we are starting from a specific to a general or specific to general to specific approaches, these are going to be studied by simulations. The estimation of—
to interrupt you.
Yes.
Yeah, I'm really sorry.
I know, I understand.
Yeah.
But so this is basically what I wanted to show you regarding the paper. I don't think I have so much, I don't have more time.
Yeah.
So thank you very much for your attention.
Thank you very much for your talk. Yeah, and sorry for the strict time constraints. Yeah.
It's okay. No worries. I knew I had this. Okay.
I think I'm gonna be in the same struggle now, but I also try to restrict myself. Yeah, so I start right away. The approach that I'm going to present today is a time-varying Gaussian graphical Lazoom model for the inverse of the covariance matrix for a set of financial asset returns. This is also work in progress, so I definitely appreciate comments or suggestions. I will start with some notes on portfolio modeling and why we think in this context it is sensible to work with the precision matrix, and then I give some empirical motivation for the adaptive lasso approach that we suggest. So, yeah. So clearly, when we construct financial portfolios, unless we consider very simple allocations like the equally weighted portfolios, the portfolio construction is always based on the interdependencies among the data, among the correlation structure of the data. The most prominent examples that you probably all know is the global minimum variance portfolio and the mean variance optimal allocations, which you obtain as the solution to these plug-in strategies that we see here, based on a given financial covariance matrix sigma, or an estimate thereof in practice. So what we now say is, if we look at these formulas, yes, they are a highly nonlinear function in the covariance, but for example, the GMVP weights are a scaled linear function of the inverse of the covariance matrix. Yeah, so if we consider the precision matrix instead, then it is much easier to interpret. The the weights and also how they are related to the precision matrix, and particularly if we want to impose restrictions like penalties on the amplitude of the GMBP weights, short selling, etc., then we can directly connect them to the elements or blocks of elements of the precision matrix. On top of that, if it comes to high-dimensional applications, then typically sparsity is something that we need to take into account. We need to lower estimation noise and so on. So we sometimes impose kind of hard restrictions on the covariance metrics. However, even if you go to dimension 200 or 300, it is very unlikely that indeed two assets in this basket of assets are indeed completely uncorrelated, so that you have a zero in the covariance matrix. If you consider the precision matrix instead, and if you have a Gaussian assumptions for returns, then a zero entry in the precision only requires that the assets are conditionally independent, which is much more realistic, especially if we have large industry sectors in which we have many similar assets. So this is why we favor to use the precision matrix. Okay. When I talk about the high dimensionality, I come to my motivation from the empirical side for our adaptive Laszlo approach that I'm going to introduce. So especially if we consider very long time horizons, here we see a time frame, an out of sample period of 1980 to 2019. Then it is very unlikely that two approaches have the same relative forecasting performance over this long time horizon. So especially when we talk about sparsity, and maybe we talk about whether a dynamic or static model is better, this depends pretty much on the economic phase that we are in, and the longer the time horizon, the more variation we have in these economic states that we encounter. What you see here is the relative forecasting performance of two of the most successful static and dynamic approaches, namely the DCC with nonlinear shrinkage, as well as the Ledoit and Wolf nonlinear shrinkage estimate of the empirical covariance matrix. The blue line is also the test statistic of the so-called fluctuation test of Giacomini and Rossi, in which we test the null of an equal forecast performance over the complete time horizon. It's not that surprising that we have so if it crosses the critical values once, then we have a rejection. So that's not that surprising that the models do not perform equally well over this long time horizon. However, the interesting part here is that this line is not really stable. So we see here we have in the beginning, the DCC is superior to the nonlinear shrinkage. Then we have an increasing, a decreasing, and we don't really have a straight line here for our relative forecasting performance. So to quantify that, we also conducted the related test, also proposed by Giacomini and Rossi, a so-called one-time reversal test, which tests for a reversal in the relative forecasting performance. The test rejected the null only at a 10% level. A problem of this test is that if there are potentially more than one reversal or change point in the time series, then it loses power. But what the test was able to detect as well, and that's the interesting part, is that we have a reversal, and we have no indication that one of the model is constantly superior over the full sample. And this leads us to the conclusion that it might be sensible to use either something like a forecast combination or a forecasting scheme in which we have something in between a dynamic and a static model, depending on in which state of the economy we are, right? So finally, our approach, adaptive time varying graphical Lazoo. So the baseline model is borrowed from a paper of Halak and co-authors from the year 2017, who start from the standard graphical Lazoo model for precision matrices, and they extend it to a time varying dimension. We do not really have a as a dynamic model for the conditional distribution of the covariance or for the precision, like for the DCC. But we say the complete joint distribution of the returns is stable for a fixed period of time, and then we have a change point, and then in the next timestamp it's again stable for a specific number of time periods. So what we can do with this approach is, we can augment it by several penalty functions. So we can tailor the type of penalty to this approach to our specific problem. Here we have the example of GMVP prediction. So what we will show in my empirical application is an additional loss function was imposed, which regularizes, which imposes an additional L2 norm on the weights of the GMVP, even though we actually model the precision matrix here. So we are not restricted to the classic L1 or L2 penalties on the precision matrix itself. And finally, and that's then now our connection to the previous slides, we suggest a dynamic recalibration scheme for the penalty parameters, such that we indeed have a relatively fast adaptation to the economic period that we enter at that point in time. A little bit more details, if time allows, sorry. How does the model look like? So we have a sample of dimension t, and we slice this sample into each n tau periods for which we assume the distribution to be stable. Yeah, so this gives us an empirical covariance estimate as tau for the respective slice, tau a sample mean of mu, and what we want to infer is theta tau, which is the precision at this point in time. So if we now condition, so we're not interested in the mean, we just condition on mu tau, we omit the constants, then we can write our Gaussian likelihood here just as the sum of the, to be proportional to the sum of the likelihood log likelihood contribution, which looks like that. So we have this representation here scaled by the number of observations that we have for each slice. Now in our empirical application, we say all slices are equal to 150 periods, but in general, of course, we are not restricted to have equal slice lengths, and that's something that we might want to explore in the future. The minimization problem then takes this log likelihood, the negative of the log likelihood, because we have a minimization problem as usual, and it augments this negative log likelihood in two directions. First, we add a set of penalties psi j for the structure. So this is then like in the standard Lazou case, we regularize the overall structure of our theta j's. And then we have the second part, and this is the new part for the time varying graphic in Lazou, is that we have additional loss functions psi tilde m, where we actually penalize differences in subsequent timestamps of theta. So theta tau minus theta tau minus 1. So what we could here address is, for example, turnover, something like that. Okay. So next slide. So here we have a slide regarding the optimization scheme. Again, we do not have time for all the details, just the most important point here. We utilized a relatively new optimization approach, which is called the alternating direction method of multipliers. It is an iterative scheme building on a Lagrange type optimization. So we had set up a Lagrange function, and then we iteratively, separately optimize several subblocks of the system. The subblocks are here our likelihood contributions and the respective penalties. And this ADMM approach has two big advantages. First of all, it is guaranteed to converge if we use only strictly convex functions. So the negative likelihood is convex in the precision, and the loss functions are only to be restricted to be strictly convex, and then we could add as many as we want to. And the second thing, due to this blocking, we can parallelize over the blocks, and this makes this this optimization scheme comparably fast, which is in practice actually the bottleneck of this whole procedure. Yeah, it leads me to the loss functions that we impose. I said already we can impose in principle any loss function which fulfills the convexity property. The problem is we need to do that many times until we have reached the convergence. So what we want is only loss functions or penalties with closed form solutions. Yeah? So we do not want to rely on some other numerical optimizer, something like that. We want a closed form solution. And what we do for the moment is that we for the time variation, we use the penalty suggested by the authors in Halak and co-authors, which is a simple element-wise L1 penalty on the elements of the precision. The same we do also for our overall structure, with one difference here: we omit the diagonal elements because it's not really sensible to penalize the diagonal elements in a precision matrix. On top of that, we augment the time varying graphical lasso by a loss function that approximates a true penalty on the GMBP weights. Yeah? So the GMBP weights itself are not convex in theta in our precision matrix, so we need to rely on an approximation. But in the paper we show that this loss function indeed helps to reduce the amount of the variation in the GMBP weights, the true penalty of our portfolio weights. All right, so I think I have time for the empirical application. So what have we done? We look at 50 years of daily asset returns from the US stock market. At the moment, we work with this cross-dimensional size of 100. And we pick for each estimation window the largest of these stocks. Yeah? So this means that at the end of each sample period, we look at, we have a database of, say, thousands of stocks, and then we pick the 100 with the largest market capitalization at this point in time, which is common practice, so that we get a slowing varying asset universe, which appears sensible if we consider 50 years of data. The out of sample period consists of the years 1980 to 2019. We already saw it on one of the first slides, which clearly includes all kind of economic periods that you might think of in the last 40 years, except for the COVID crisis, maybe. Then we re-estimate all models every 21 days, and also the dynamic models are only reallocated, so the portfolios are only reallocated every 21 days, because otherwise we would achieve an unreasonable amount of turnover, which we want to avoid. The out of sample exercise is in a rolling window scheme, 5 years estimation window. For our approach, we additionally have a calibration period of 1 year. To make a fair comparison, I should say we would also need to allow the benchmark models to have a 6-year estimation scheme, but we found that in the out of sample comparison, they actually performed better with only 5 years estimation. So the comparison is, I think, still quite fair. And for the moment, we just compare our lasso approach with the DCC and the nonlinear shrinkage static approach. Okay. How does this calibration scheme look like? This is actually my favorite slide. I tried to wrap it up in 1 minute. So the problem that we have is typically when you calibrate parameters in such a setting, you have a training period and a testing period. Here we additionally have the time dimension, so we obviously cannot ignore the time structure in our data. So we adapt classic calibration schemes for parameters to this time dimensional setting. And we do that by, say, we start with a rolling window 1,250 observations. We make out of sample forecast comparisons for evaluation for the next 21 days. We go 1 month to the future, we repeat this exercise, and so on and so on, such until we have reached 1 year of out of sample observations. And then out of all parameter constellations that we have, we use a grid of 15 times 15 times 15 for our 3 parameters. We pick that constellation with the best, the lowest variance, in this case, the best out of sample periods of the last year, and use that for our first out of sample prediction. Then we roll everything 1 month ahead, continue this procedure, and so on, such that we always have a rebalanced set of parameters every month, like in a dynamic model, kind of. Okay. So what does the timing say? Okay, maybe 30 seconds. Just a quick glance on our results. They are preliminary. We had a shutdown with our high performance computer at the university, so I can only show you results until the end of 2004. What we see here is what we were expecting, or what we were hoping to expect, is that if you look at the cumulative loss differences, our approach compared to both the static and the dynamic model performs moderately well. Yeah, so we always have this negative slope. There's one exception, and this exception almost destroys any kind of these forecasting experiments, which is the Black Monday in October 87. Yeah, so we have an extreme loss comparison to the DCC because it is still faster to adapt than our model. However, except for this period, we have this negative slope here. And also we see, if we look at the full sample and at 5-year subsamples, our model is the only one to be included always in the model confidence set so far. And except for this example with the 87 included, outperforms both approaches uniformly well. And this is also my conclusion for the model. It is very flexible, it is very sparse at the same time, and of course, yeah, there's still much to do. So what we're planning is extend the approach to other settings, especially other concentration ratios of cross-sectional per time, per estimation units, use a broader class of loss function, especially the turnover is something that we want to explicitly attack in the next step. And then we might also want to apply it to other portfolio allocations, like the mean variance of portfolio, or even other, potentially even other financial problems where we can use this model for the precision matrix. Okay, yeah, thank you very much. Yeah, I also used my time. I'm advised to close the session, but if there are questions, I would, yeah, we can discuss them. Yeah, I'd be really open to that, maybe outside of the session. So if this is not the case at the moment, then I thank all the participants for joining us in this session on time varying volatility. And I wish you all a nice remainder of the day and of the conference. See you soon.
Thank you, Laura. Bye.
Thanks.
Goodbye.
Thank you.